Rethinking the drone. 10 engineering architectures that could redefine aerial systems. For more than a decade, drones have been associated with a fairly small set of uses. Most people think of aerial photography, mapping, surveillance, package delivery, or industrial inspection. These applications have shaped how drones are designed and how the public understands them. From an engineering perspective, however, this view is limiting. A drone is not fundamentally a camera platform, nor is it simply a small aircraft. At its core, a drone is something much more basic and versatile. A drone is a mobile energy conversion system that can move freely in three-dimensional space. It takes stored energy and converts it into thrust. That thrust allows the system to control its position. Once positioned, it can perform a task. Seen this way, the drone itself is not the product. The product is what the drone is able to do because it can place energy, tools, sensors, or materials precisely where they are needed in space. This shift in thinking matters. When drones are treated mainly as flying gadgets, innovation tends to focus on small improvements. Cameras get better, batteries last longer, flight controllers become more stable. These upgrades are valuable, but they do not change the fundamental role drones play in larger systems. If we instead view drones as programmable physical nodes in the air, the design space opens up dramatically. Drones can become part of broader engineering systems that interact with infrastructure, energy networks, manufacturing processes, and even each other. In this framework, a drone is closer to a robotic platform than a consumer device. It is a tool that can carry sensors, manipulate objects, transport energy, deploy materials, or coordinate with other machines. Its value comes from mobility, precision, and the ability to operate where fixed infrastructure cannot easily reach. This perspective encourages engineers to rethink the architecture of aerial systems themselves. Instead of asking how to improve a typical quadcopter, the question becomes, what entirely different structures could aerial robotics take? For example, drones could be designed to operate in coordinated swarms rather than as individual units. They might exchange power, share computational tasks, or distribute sensing across large areas. Other designs might integrate drones directly into physical infrastructure, allowing them to dock, recharge, or become temporary extensions of buildings and networks. New architectures might also rethink how drones handle energy. Instead of carrying all their power on board, they could harvest energy from the environment, receive power wirelessly, or operate in relay systems where multiple drones support one another. Materials and structural design offer another direction. Future drones may not resemble today's rigid frames at all. They could be modular, morphing, or capable of assembling themselves into larger structures when needed. These possibilities show that drones are still early in their technological evolution. The familiar quadcopter design is only one solution among many. The following 10 architectures explore how aerial systems could be redesigned from the ground up. Each concept represents a structural shift in how drones interact with energy, infrastructure, materials, and distributed networks. Rather than incremental improvements, these ideas point toward entirely new ways of thinking about aerial robotics. The Perch-and-Print structural repair drone. Airborne 3D printing is often discussed as the next big step in aerial robotics. In theory, a drone could fly to a damaged structure and print new material directly onto the surface. It sounds straightforward, but the idea is widely misunderstood. The difficulty is not the printing technology itself. Material extrusion, the core method used in most 3D printers, is already well developed. Printers can deposit plastics, resins, concrete, and other materials with high precision. The real obstacle is mechanical stability. Flight is naturally unstable and requires constant energy to maintain position. Even with advanced control systems, a hovering drone experiences small movements from wind, propeller turbulence, and control corrections. These movements are normal in flight, but disastrous for precision manufacturing. 3D printing, by contrast, depends on rigidity. A printhead must follow very precise paths while maintaining consistent distance and alignment with the surface being printed. Even small vibrations or positional drift can ruin a layer or weaken the structure. This conflict between flight and precision is why the concept of hovering 3D printing drones rarely works well in practice. A more practical architecture changes the problem entirely. Instead of printing while hovering, the drone lands on the structure and physically attaches itself to the surface. This is done using articulated gripping mechanisms, such as robotic claws, magnetic feet, or clamping arms. Once the drone locks onto the structure, the system transfers its load away from the propulsion system and into the structure itself. The drone is no longer fighting gravity through its propellers. Instead, it becomes mechanically supported by the object it is working on. This approach works especially well on large structures such as wind turbine towers, bridge beams, transmission pylons, or building facades. After attachment, the system transitions into a different operating mode. During flight, the drone relies on flight controllers and PID loops to maintain stability. Once perched, those controls become secondary. The drone switches to fine-resolution motion control, similar to a robotic arm or a CNC machine. Propeller output drops dramatically, reducing turbulence and vibration. Mechanical dampening systems isolate sensitive components from residual movement. In some designs, the propellers may shut off entirely once the drone is securely attached. Power systems can also change during this phase. Electrical contact pads could allow the drone to draw power directly from the structure, from nearby infrastructure, or from a tethered supply. This reduces battery constraints and allows the repair operation to run longer. At this stage, the machine is no longer functioning as a flying vehicle. It has effectively transformed into a temporary surface-mounted robotic manufacturing unit. This distinction is important. The system should not be thought of as a drone that prints while flying. Instead, it is a mobile repair robot that uses flight only to reach locations that are otherwise difficult or dangerous for humans to access. Once in place, it behaves more like a precision industrial machine than an aircraft. This architecture opens new possibilities for maintaining large infrastructure. Bridges, towers, offshore platforms, and tall buildings often require expensive scaffolding, cranes, or human climbers for repairs. A Perch-and-Print drone could reach the site quickly, attach itself, and carry out localized structural repairs with minimal setup. In this system, the real engineering challenge is not printing technology. The key problems lie in load transfer, vibration isolation, secure attachment, and automated positional locking that allows the machine to work safely and accurately at height. Variable buoyancy hybrid drone. Most multi-rotor drones operate in the same basic way. Their motors spin constantly to push air downward, generating lift that keeps the aircraft in the air. Every second the drone is flying, it is actively fighting gravity. This approach works, but it is inherently inefficient. Nearly all the stored energy in the battery is spent simply keeping the drone airborne. Only a small portion of that energy goes toward the actual mission, whether that is carrying sensors, inspecting infrastructure, or transporting cargo. In engineering terms, the system is spending most of its energy maintaining lift rather than performing useful work. A different architecture approaches the problem from another angle. Instead of relying entirely on propulsion for lift, the drone can use variable buoyancy to support part of its weight. This is done by integrating a controllable gas chamber into the drone's structure. The chamber can be filled with a lighter-than-air gas such as helium, or in some designs, air that is heated to reduce its density. The buoyant force created by this chamber helps offset the mass of the drone. If buoyancy supports a significant portion of the weight, the motors no longer need to generate full lift. For example, if buoyancy offsets 60% of the system's mass, the propellers only need to handle the remaining 40%. Their main role shifts towards stabilization and directional control rather than constant heavy lifting. This redistribution of forces changes how the entire aircraft behaves. First, the propulsion system experiences much lower mechanical strain. Motors operate at lower power levels and do not need to spin at maximum speed for long periods. This reduces wear and heat generation, which can improve reliability. Second, the drone becomes quieter. Because the propellers are not working as hard, they produce less noise. A lower acoustic signature can be useful for environmental monitoring, urban operations, and other situations where loud rotor noise is undesirable. Third, endurance can increase dramatically. When the motors consume less power, the same battery capacity can support much longer flight times. Missions that normally last 30 minutes could potentially extend to several hours depending on the design. Despite these advantages, hybrid buoyancy systems introduce new engineering challenges. The most obvious issue is buoyancy control. Gas expands and contracts as altitude and temperature change. If the internal pressure of the buoyancy chamber is not carefully managed, the lift produced by the gas can vary in unpredictable ways. To maintain stability, the system must monitor environmental conditions and adjust the internal pressure of the gas chamber in real time. Or thermal controls may be required to keep buoyancy within a safe range. Another challenge is the center of gravity. Gas chambers take up space and can shift the mass distribution of the aircraft. As the drone moves, accelerates, or changes orientation, the balance of forces must remain stable. Active flight control systems must compensate for these shifts. Safety also becomes more complex. If the buoyant gas leaks or escapes, the aircraft must still be able to descend safely. Emergency descent protocols need to account for partial buoyancy loss without causing sudden instability or uncontrolled drops. Because of these factors, the concept should not be seen as replacing rotors with balloons. Instead, it is a hybrid system that combines buoyant lift with traditional propulsion. The goal is simple: redistribute how energy is used. By allowing buoyancy to carry part of the load, the drone's motors can focus on control and maneuvering. This change could significantly extend flight duration and open new operational possibilities for aerial systems. Deployable solar canopy infrastructure drone. In disaster zones and remote field operations, two needs appear almost immediately: power and shelter. Medical teams need electricity for equipment. Communication systems require reliable energy. At the same time, responders often need shade or weather protection while working in exposed environments. Traditionally, these needs are handled with separate systems. Portable generators are transported in. Tents or canopy structures are assembled on the ground. This works, but it takes time, manpower, and logistical coordination. An alternative approach is to combine these functions into a single aerial system. A deployable solar canopy drone would act as a mobile platform capable of delivering both temporary shelter and renewable power generation. Instead of simply carrying supplies, the drone itself becomes the structure that provides them. The concept centers on a flexible photovoltaic membrane integrated into the drone's body. During flight, this membrane remains compact and folded to maintain aerodynamic stability. Once the drone reaches its destination, the system deploys the membrane using telescopic radial arms. As these arms extend outward, the membrane unfolds into a large canopy shape. Tensioning mechanisms pull the material tight, creating a stable surface that functions both as a solar panel array and as an overhead shelter. The result resembles a lightweight umbrella or pavilion suspended in the air or anchored above a small operating area. This canopy performs two important functions at the same time. The photovoltaic surface captures solar energy, while the canopy structure provides shade and limited weather protection for people or equipment below. Although the concept sounds straightforward, the engineering challenges are mostly mechanical. One of the first challenges is controlled deployment. When a large flexible membrane unfolds from a compact drone body, there is a risk of torsional instability. Twisting forces can cause the material to tangle or deploy unevenly. The extension arms and tensioning system must ensure the canopy opens smoothly and symmetrically. Wind resistance is another major factor. Once deployed, the canopy increases the surface area exposed to the environment. Even moderate wind can introduce large aerodynamic forces. The drone must stabilize the structure either by active rotor control, tensioned anchor lines, or partial ground attachment. Solar orientation also matters. For photovoltaic systems to generate useful power, they must face the sun at an efficient angle. This means the canopy may need a tilt adjustment mechanism or rotational control so that the solar surface can track the sun's position during the day. Once the canopy is fully deployed, the drone's role changes significantly. Instead of acting as a fast-moving aerial vehicle, the system becomes a static energy node. Its propellers may reduce power output or operate only for stabilization. The main function is now energy generation and distribution rather than mobility. The electricity generated by the canopy can be delivered in several ways. Power could be transmitted through a tether cable to equipment on the ground. In more advanced systems, wireless power transfer might support nearby sensors, communication relays, or portable medical devices. This architecture reframes the role of the drone. The drone itself is not the final objective. Its purpose is to transport, position, and deploy a piece of temporary infrastructure that can support operations in difficult environments. In disaster response scenarios, such a system could quickly establish a shaded work area with built-in solar power. In remote research sites, it could provide temporary energy for sensors or communication systems without requiring heavy ground equipment. By combining mobility with deployable infrastructure, the drone becomes a rapid response tool for building small but useful systems exactly where they are needed. Rail-assisted hybrid mobility drone. Many infrastructure inspection tasks follow long, predictable paths. Power transmission lines stretch across mountains and fields. Pipelines run for hundreds or even thousands of kilometers. Railway corridors and elevated transport systems follow fixed routes. Drones are already used to inspect these types of infrastructure. They capture images, scan for damage, and collect sensor data along the way. However, using a drone for these inspections often means flying continuously along a straight path. From an engineering standpoint, this is inefficient. Multi-rotor drones consume a large amount of energy simply to stay in the air. When they travel long distances, the propulsion system must work constantly to generate lift, maintain stability, and move forward. Much of the battery capacity is spent just keeping the drone airborne rather than performing the inspection itself. For missions that follow fixed linear routes, there may be a better option. A rail-assisted hybrid mobility drone introduces a different architecture. Instead of flying the entire route, the drone can attach itself to a lightweight guide rail installed along the inspection corridor. Once attached, the drone transitions from thrust-based flight to rolling movement along the rail. In this mode, the system behaves less like an aircraft and more like a small robotic vehicle moving along a track. Wheels or rollers allow the drone to travel smoothly along the rail with minimal friction. The motors that normally power the propellers are no longer responsible for carrying the drone's weight. This shift dramatically reduces energy consumption. When the drone is supported by the rail, gravity is no longer a problem the propulsion system must constantly fight. The motors only need to provide small bursts of power for movement and stabilization. In calm conditions, the propellers may remain idle or run at very low power. The drone still retains full flight capability when needed. If it encounters an obstacle, a damaged section of rail, or an area that requires closer inspection, it can detach from the rail and switch back to normal flight mode. This creates a dual-mode mobility system where flight is used only when necessary. Several engineering elements are critical for making this architecture work. One of the most important is the alignment and latching mechanism. When the drone approaches the rail, it must be able to position itself accurately and lock onto the track without human assistance. Sensors, vision systems, or magnetic guides may help the drone align itself with the rail before engaging the latch. Once connected, the system must hold securely even in wind or vibration. The locking mechanism needs to support the drone's weight while still allowing smooth rolling motion. The drone must operate with two very different movement systems. In flight mode, the controller manages propeller thrust and orientation. In rail mode, the system must control wheels or rollers while maintaining balance and sensor orientation. A reliable switching system between these two modes is essential. Safety also requires redundancy. If the rail connection fails or the system loses alignment, the drone must be able to detach quickly and return to stable flight. This ensures that a mechanical problem does not lead to a crash. The most important idea behind this architecture is simple. Flight is treated as an intermittent capability rather than the default mode of operation. Instead of trying to improve efficiency only through better batteries or more powerful motors, the system improves efficiency by changing how mobility works. By combining rails with aerial capability, the drone uses the most energy-intensive method, flight, only when it truly needs it. The result is a more efficient inspection platform for long, linear infrastructure networks. Fire suppression and surface reinforcement drone. Traditional firefighting usually begins after a fire has already grown large enough to be visible and dangerous. By the time emergency crews arrive, flames may have spread across wide areas, making containment difficult and costly. A different strategy focuses on stopping fires much earlier. Many fires begin as small ignition points. A spark from damaged electrical equipment, overheating machinery, or dry vegetation can start a localized burn that slowly spreads. If these early ignition points could be detected and neutralized quickly, many large fires might never develop. A specialized aerial system could make this possible. A fire suppression and surface reinforcement drone is designed to respond to fires at their earliest stages. Instead of only reacting to large flames, the system monitors environments for heat signatures that indicate potential ignition. The architecture of this system is built around 3 connected modules that operate in sequence: detection, suppression, and reinforcement. The first module is thermal detection. The drone uses infrared imaging sensors to scan surfaces and identify abnormal temperature patterns. Unlike normal cameras, infrared sensors detect heat differences, making it possible to spot hotspots even when flames are not yet visible. For example, an overheating electrical component on a power pole, a smoldering section of dry vegetation, or a hot surface on industrial equipment could all trigger the system's attention. Once the drone identifies a suspicious thermal signature, it moves closer to confirm the source. Onboard processing systems analyze the heat profile to determine whether the hotspot represents a genuine fire risk. If intervention is required, the system activates the second module, targeted fire suppression. Instead of releasing a large volume of extinguishing material like a traditional fire hose, the drone uses directional aerosol sprays or microcapsule suppression agents. These materials are designed to interrupt the chemical reaction of combustion quickly while minimizing waste. Because the drone can position itself precisely above the ignition point, only a small amount of suppressant may be needed. This targeted approach allows the system to deal with small fires rapidly, without creating large amounts of residue or water damage. However, simply extinguishing a flame does not always solve the problem. Many surfaces that ignite once are likely to ignite again if the underlying heat or material conditions remain unchanged. For this reason, the system includes a third stage, surface reinforcement. After the suppression phase, the drone applies a thin layer of fire-resistant coating to the affected area. This coating may be extruded as a liquid or gel that quickly bonds to the surface. It forms a temporary barrier that reduces the risk of reignition. Managing these stages requires careful coordination. One key challenge is temperature control. If the reinforcement material is applied while the surface is still too hot, it may fail to adhere properly or degrade before it sets. The drone must continuously monitor surface temperature to determine the correct moment to apply the coating. Material properties also matter. The reinforcement compound must maintain the right viscosity so it can spread evenly while still bonding to surfaces that may be warm, uneven, or partially damaged. Because of these factors, the system functions as a closed-loop intervention platform rather than a simple aerial extinguisher. Sensors identify potential fires. Suppression systems eliminate the immediate threat. Reinforcement materials stabilize the surface and reduce the chance of another ignition. By combining detection, response, and prevention in a single cycle, the drone becomes a tool for early fire management rather than only emergency reaction. Inverted tunnel inspection drone. Inspecting underground spaces presents a unique set of challenges for aerial systems. Tunnels, mines, utility corridors, and underground transport routes often have tight clearances, unpredictable air movement, and limited visibility. Perhaps the biggest limitation is the absence of GPS signals, which most drones rely on for stable navigation. In these environments, conventional flight becomes difficult and inefficient. Standard drones depend on continuous lift from their propellers to stay airborne. In confined underground spaces, that constant lift creates unnecessary energy consumption. Turbulent airflow from the propellers can also stir dust and debris, reducing visibility and potentially interfering with sensors. Another issue is safety. When drones fly close to walls or ceilings, even small navigation errors can lead to collisions. Underground environments often leave little room for recovery if a drone loses stability. A different architectural approach changes how the drone interacts with the tunnel environment. Instead of trying to maintain free flight within the tunnel, the drone attaches itself to the ceiling and moves along it. This concept turns the usual operating logic upside down. Ceiling proximity, which is normally treated as a hazard, becomes the main structural support for the system. The drone uses specialized rolling modules mounted on its upper frame. These modules make contact with the tunnel ceiling and allow the system to move forward like a small vehicle traveling along an overhead track. The propellers remain active, but their role changes. Rather than supporting the full weight of the drone, the downward-facing propellers provide stabilization and assist with traction against the ceiling. The mechanical rolling modules carry most of the load. This dramatically reduces the amount of lift the motors need to generate. Because the propulsion system is no longer responsible for keeping the drone fully airborne, energy consumption drops significantly. The drone can travel longer distances within the tunnel while using less battery power. This design also improves stability. With physical contact against the ceiling, the drone has a fixed reference surface that helps maintain consistent positioning. Small disturbances from airflow or uneven tunnel surfaces are less likely to push the system off course compared to a fully hovering drone. Navigation remains a complex problem in underground spaces because satellite signals are unavailable. To solve this, the drone relies on a combination of LiDAR scanning and inertial measurement systems. LiDAR sensors continuously map the tunnel's internal geometry by sending out laser pulses and measuring their reflections. This creates a three-dimensional model of the environment in real time. Inertial measurement units track the drone's movement, orientation, and acceleration. By combining these data sources, the system can estimate its position and maintain a stable path through the tunnel, even without external navigation signals. The drone can detach from the ceiling when necessary. If an obstacle blocks the route, or if a specific section of infrastructure requires closer inspection, the system can temporarily switch to free flight. After completing the task, it can reconnect with the ceiling and continue rolling along its route. This architecture demonstrates a broader principle in aerial robotics. Instead of forcing drones to operate in environments that are poorly suited for continuous flight, engineers can adapt the system to the geometry of the space itself. In tunnels and underground corridors, the ceiling becomes a structural advantage rather than a constraint. By combining mechanical contact with controlled propulsion, the drone becomes a more efficient and reliable inspection platform for complex underground environments. Capsule swarm deployment, mothership environmental monitoring, often requires large numbers of sensors spread across wide areas. Researchers may need to measure air quality across a forest, track temperature changes in a disaster zone, or monitor chemical conditions around industrial facilities. In theory, distributed sensor networks can provide detailed, real-time data about these environments. In practice, deploying those sensors is often the hardest part. Placing dozens or hundreds of sensing devices across difficult terrain usually requires significant manpower. Teams must travel to each location, install the devices, and ensure they are properly positioned. In remote or hazardous areas, this process becomes slow, expensive, and sometimes dangerous. An alternative approach uses aerial systems to distribute the sensors automatically. A capsule swarm deployment mothership is a large carrier drone designed to release smaller sensor units across a targeted area. Instead of acting as the main sensing platform itself, the carrier drone functions primarily as a delivery and deployment mechanism. The system carries a number of compact capsule drones inside its structure. Each capsule is small, lightweight, and tightly packed to maximize storage efficiency during flight. Once the carrier reaches the designated deployment zone, it releases the capsules into the air. As each capsule falls away from the carrier drone, it activates a small deployment sequence. The outer shell opens, and internal components unfold into a minimal autonomous unit. Small propellers or gliding surfaces help stabilize the capsule and guide it toward its landing position. After landing, the capsule becomes a stationary sensing node. Each unit contains a small set of sensors tailored to the mission. These might include temperature sensors, humidity detectors, gas analyzers, acoustic microphones, or radiation monitors. The capsules also include communication modules that allow them to transmit data and communicate with nearby nodes. Once several capsules are deployed in the same region, they begin forming a mesh communication network. In a mesh network, each node communicates not only with a central receiver, but also with neighboring nodes. Data can travel through multiple pathways across the network. If one node fails or loses signal, information can still move through alternative routes. This distributed communication structure allows the sensing network to remain functional even if some capsules are damaged or disconnected. Building a system like this involves several engineering challenges. One important issue is mechanical release synchronization. Capsules must be released in a controlled sequence so they spread across the intended coverage area. If they deploy too close together, the sensing network may become uneven or redundant. Another key challenge is the reliability of the unfolding mechanism. Each capsule must transition from a compact storage form into a working device while falling through the air. The hinges, springs, or inflatable structures involved in this process must function consistently under varying conditions. Network formation is also critical. Once the capsules land, they must automatically identify nearby nodes and establish communication links. The system must be able to build a functioning network without human configuration. What makes this architecture different from typical drone swarms is its purpose. Many swarm concepts involve dozens of drones flying together in coordinated motion. In the capsule mothership model, the small units do not remain airborne. Instead, they transform into a temporary infrastructure of sensing nodes distributed across the environment. The carrier drone's role is therefore limited but essential. It transports the capsules, positions them above the deployment area, and releases them in a controlled pattern. After the deployment is complete, the carrier drone may return to base or continue to another location. In this architecture, the drone is not the final sensing platform. It is the system that makes rapid deployment of a distributed monitoring network possible. Biomaterials Surface Reinforcement Drone. Most structural repair methods rely on rigid synthetic materials. Cracks in concrete or stone are often filled with epoxy, polymer compounds, or cement mixtures. These materials are strong and durable, which makes them useful for many industrial applications. However, rigid repairs are not always ideal. In heritage conservation, for example, historic structures are often built from materials that expand, contract, and age differently from modern repair compounds. Introducing a very rigid filler into an older structure can create stress imbalances. Over time, this mismatch can lead to new cracks or additional damage. Similar issues appear in environmentally sensitive areas. In natural rock formations, bridges, or ecological infrastructure, synthetic repair materials may disrupt the surrounding environment or degrade in unpredictable ways. A different approach looks toward bioengineered materials as part of the repair process. In this architecture, a drone delivers a biological growth substrate rather than a conventional rigid filler. The material deposited into a crack or damaged area contains microorganisms or bioreactive compounds that gradually expand and strengthen the structure over time. Instead of completing the repair instantly, the system initiates a biological process that continues after the drone has left the site. For example, some biomaterial systems use bacteria that produce calcium carbonate as they grow. When placed inside small cracks, these organisms can gradually form mineral deposits that fill the gap and reinforce the surrounding material. Other systems may use fungal networks or plant-based fibers that expand and bind within structural cavities. The drone's role is to place the biological material precisely where it is needed. Using onboard cameras and sensors, the drone identifies cracks or damaged surfaces. It then dispenses a controlled amount of the biomaterial mixture directly into the affected area. Because the material is designed to grow or expand naturally, the initial deposition can remain relatively small. Over time, the biological process strengthens the repair from within. Although the concept is simple in principle, the engineering challenges are significant. One of the main concerns is biological viability. The microorganisms or living components inside the repair material must remain alive and functional during storage, transport, and extrusion. The drone's dispensing system must handle the material gently enough to avoid damaging these living elements. Environmental conditions also play a critical role. Biological growth depends on factors such as moisture, temperature, and nutrient availability. The drone may need to deliver additional nutrients or moisture to support the growth process. Sensors can help evaluate the surrounding environment to determine whether conditions are suitable for biological reinforcement. Another challenge is predictability. Unlike rigid materials that harden quickly into a fixed form, living systems evolve gradually. Engineers must understand how the material will expand or mineralize over time, and how that process will interact with the surrounding structure. Careful modeling and testing are necessary to ensure that the biological repair strengthens the structure rather than creating unintended stress points. Despite these complexities, the potential advantages are substantial. Biomaterial repairs can adapt to the surrounding environment and integrate more naturally with existing structures. In heritage buildings, this can preserve historical materials without introducing harsh synthetic compounds. In natural environments, the repair process can remain compatible with local ecosystems. This architecture brings together several different fields. Robotics provides the mobility and precision needed to reach damaged areas. Material science contributes the engineered substrates that initiate the repair process. Biotechnology enables the biological growth that completes the reinforcement over time. In this system, the drone does not perform the entire repair itself. Instead, it acts as a delivery vector for living reinforcement systems, initiating a process that continues long after the drone has finished its mission. Indoor microclimate shaping drone network. Large indoor spaces often struggle with uneven environmental conditions. Warehouses, factories, data centers, and large event halls can experience problems such as poor airflow circulation, temperature layering, or pockets of trapped gases. These issues are usually caused by the size and geometry of the space. Warm air naturally rises, creating thermal layers where the ceiling becomes much hotter than the floor. Ventilation systems may not distribute air evenly across the entire facility. In some industrial environments, gases or fine particles can accumulate in certain zones because air currents are weak or poorly directed. Traditional solutions rely on fixed infrastructure. Large fans, ventilation ducts, and HVAC systems are installed to move air around the building. While these systems are effective, they have limitations. Once installed, their airflow patterns are mostly fixed. Adjusting them often requires manual changes or mechanical upgrades. A different approach treats airflow as something that can be actively shaped in real time. An indoor microclimate shaping drone network uses multiple drones working together to influence air movement inside a building. Instead of acting as transport devices or inspection tools, the drones function as mobile airflow actuators. Each drone is equipped with air velocity sensors, temperature sensors, and environmental monitors. These sensors allow the system to measure local airflow patterns and identify areas where conditions are uneven or problematic. The drones then use their propellers not just for flight, but also to intentionally redirect air currents. By adjusting their position and thrust direction, drones can push air from one region of a facility toward another. For example, if warm air accumulates near the ceiling, drones can help circulate it downward to mix with cooler air below. If a section of the building has stagnant air, the drones can create artificial airflow to improve ventilation. In this way, the drones do more than move through the air. They actively reshape how air moves through the environment. To make this possible, the system relies on computational models of airflow. Algorithms based on computational fluid dynamics, CFD, analyze sensor data and predict how air currents will behave when influenced by the drone's propellers. These algorithms help determine where drones should position themselves and how their thrust vectors should be oriented. By coordinating their actions, the drones can influence airflow across a large indoor space. This transforms the drone's role entirely. Instead of carrying sensors or equipment, the drone itself becomes a tool for manipulating fluid dynamics. The propellers act like adjustable fans that can be repositioned anywhere in the facility. Controlling such a system presents several challenges. One major challenge is cooperative optimization. Because multiple drones operate at the same time, their airflow effects can interact in complex ways. If not carefully coordinated, the drones might cancel each other's influence or create unwanted turbulence. Turbulence management is another concern. Rapid propeller movements can introduce chaotic air patterns that interfere with the intended airflow direction. Control algorithms must balance airflow shaping with maintaining smooth circulation. Continuous environmental feedback is also essential. Airflow conditions change constantly as machinery runs, doors open, or people move through the space. The drone network must constantly monitor these changes and adjust its positions accordingly. When functioning properly, the system turns the air itself into something that can be managed dynamically. Instead of relying entirely on fixed ventilation hardware, the building gains a flexible layer of environmental control. The drones act as distributed propulsion nodes that can shape airflow wherever it is needed. In this architecture, indoor climate becomes partially programmable through coordinated aerial systems. Dynamic Aerial Safety Perimeter System. Safety barriers are a standard feature in construction sites, industrial facilities, and hazardous work environments. Fences, cones, warning tape, and temporary barricades are commonly used to mark areas that workers should avoid. These barriers help prevent accidents by creating clear physical boundaries around dangerous zones. However, traditional safety barriers have one major limitation. They are static. Once installed, fences and barricades remain fixed in place until someone physically moves them. In fast-changing environments such as construction sites, work zones can shift throughout the day. Machinery may move, excavation areas expand, and temporary hazards appear in new locations. Updating safety barriers in response to these changes often requires manual effort. Workers must relocate cones, rebuild temporary fencing, or adjust warning markers. During the time between a hazard appearing and the barrier being moved, people may unknowingly enter dangerous areas. A dynamic aerial safety perimeter system offers a more flexible approach. Instead of relying entirely on physical barriers, this architecture uses drones to create a mobile safety boundary around hazardous zones. Multiple drones hover or patrol in a coordinated formation that defines the perimeter of a restricted area. The drones act as visible and digital markers of the boundary. Each drone maintains its position relative to the others, forming a geometric shape that outlines the restricted zone. The formation might take the shape of a circle, rectangle, or irregular polygon, depending on the environment and the size of the hazard. Workers nearby can clearly see the drones in the air, which provides a visual indication that the area is restricted. At the same time, the system can interact with wearable safety devices. Workers may carry helmets, vests, or wristbands equipped with ultra-wideband positioning technology. These devices communicate with the drones and track the worker's distance from the safety perimeter. If someone approaches too closely, the wearable device can issue warnings, such as vibration alerts, audio signals, or visual notifications. This gives workers immediate feedback before they cross into a dangerous area. If a person continues moving toward the boundary, the system could trigger stronger alerts or notify supervisors in real time. One of the most valuable features of this system is its adaptability. In construction and industrial environments, hazardous zones often change as work progresses. A trench may expand, a crane may begin operating in a new area, or heavy equipment may create temporary danger zones. With a drone-based system, the safety perimeter can be recalculated automatically. As soon as a hazard location changes, the drone formation adjusts its positions to match the new boundary. This process can be controlled through site management software or automated hazard detection systems. Because the drones move dynamically, the safety boundary remains accurate even as the physical environment changes. This approach introduces the idea of programmable safety zones. Instead of building fixed barriers, site managers define restricted areas digitally. The drone network then translates those digital boundaries into visible and monitored space within the physical environment. The drones themselves are not the hazard and not the protection. Their main role is to define where the boundary exists. In this architecture, the drones do not simply occupy space, they define space. By combining aerial positioning, wearable sensors, and real-time control systems, a dynamic aerial safety perimeter can provide a flexible and responsive layer of protection in environments where safety conditions constantly evolve. Engineering themes that connect these architectures. At first glance, the 10 drone systems described earlier may seem very different from one another. Some focus on infrastructure repair, others on environmental monitoring, energy generation, or safety management. The specific applications vary widely. However, when examined from an engineering perspective, these systems share several underlying principles. These common ideas point toward a broader shift in how aerial systems may evolve in the future. Mode transition. One recurring pattern is the ability of drones to move between different operating states. Traditional drones are designed to remain in flight for most of their missions. Their propellers constantly generate lift while the drone moves through the air. In many of these architectures, flight is only one phase of operation. The drone may fly to a location, then attach to a surface, roll along a structure, or remain stationary while performing a task. For example, a repair drone may perch on a bridge beam before beginning its work. A tunnel inspection drone may latch onto a ceiling and move along it mechanically rather than hovering. This ability to transition between modes allows the system to operate more efficiently and with greater stability. Energy redistribution. Another common theme is the effort to reduce the amount of energy spent on maintaining lift. In conventional drones, a large portion of battery power is consumed simply to keep the aircraft airborne. This limits flight duration and restricts the amount of equipment the drone can carry. Many of the architectures described earlier address this problem not by increasing battery capacity, but by changing how energy is used. Some designs rely on buoyancy to offset part of the drone's weight. Others allow the drone to anchor itself to structures so the propulsion system can reduce output. Hybrid systems may switch between flight and mechanical movement to conserve power. By redistributing the energy demands of the system, these designs extend operational capability without relying solely on larger batteries. Structural interaction. Another important shift involves how drones interact with the physical environment. Most current drones try to avoid contact with surrounding structures. They hover near objects while maintaining a safe distance. This approach simplifies flight control but limits what the drone can do. In the architectures described earlier, drones often engage directly with infrastructure. They grip surfaces, attach to structures, roll along rails, or deploy materials onto physical objects. Instead of remaining isolated in the air, the drone becomes mechanically connected to the environment it is working on. This direct interaction expands the range of tasks drones can perform. Distributed intelligence. Several of these systems also rely on networks of drones rather than single units. When multiple drones operate together, they can divide tasks, share sensor data, and coordinate their movements. Capsule deployment systems can create distributed monitoring networks. Airflow management drones can collectively influence indoor environments. Safety perimeter drones can form coordinated boundary formations. In these cases, the capabilities of the overall system emerge from cooperation between many smaller units. System-level thinking. Perhaps the most important theme is a shift towards system-level design. In many traditional applications, the drone itself is treated as the final product. It carries a camera, performs a survey, and returns with the collected data. In the architectures explored here, the drone is only one component within a larger system. It may act as a delivery mechanism, a positioning platform, or a mobile actuator within a broader network of technologies. The real value lies in how the drone interacts with other systems, materials, and infrastructure. Conclusion: the future of drone technology is unlikely to be defined only by better cameras, longer flight times, or faster processors. The more significant changes will come from rethinking how aerial systems are designed and how they interact with the world around them. At their core, drones are machines that convert stored energy into controlled movement through space. This mobility gives them advantages that ground-based systems often cannot match. When that mobility is combined with anchoring mechanisms, buoyancy systems, distributed networks, and advanced materials, drones begin to take on a different role. They stop being simple flying devices. Instead, they become mobile infrastructure platforms capable of interacting with physical environments in new ways. The next generation of aerial systems may therefore be defined less by flight itself and more by how intelligently these machines connect with the structures, materials, and systems around them. Progress will come not only from better propellers or batteries, but from better system architecture.